do is repeat that about 9 more times. Here's a 10.2 minus 2.55 for y. Let's drop it again and get a measurement. About 15.0 and 7.35. And a couple for the length, 7.30 to 19.90. And then 10.75 to 23.45. Now, once you've got your data into, once you've collected your data from the experiment, you can stick that data into a spreadsheet program or work it out by calculator. The lengths are all going to be, let's actually make it absolute value because I didn't specify which one should be bigger and which one should be smaller, but we will want a positive value in all our lengths. So I can copy that down. Whoops. I'll go ahead and do this one too. Equals absolute value of this number times this number. And you can see, really, what did I do? 26. Oh, I multiplied instead of subtracting. Okay. Okay, so then I can copy both of those down and get the length and width from the different trials. Now, it can be noted that these two x's are connected and these two y's are connected, but really this measure of length is not connected in any intrinsic way to that measure of width. So these are distinct trials of length and width. So it wouldn't be quite correct to say, I mean, we could say we did 3 trials of the area equals this times this, and copy that down. And then, oops, copy that. So I'm going to talk for a moment here about the mean standard deviation dot sample and the standard error. So the mean of these 3 values equals the arithmetic average of those 3 values. The standard deviation dot s is stdev dot s of those 3 values. And the standard error is going to be the standard deviation dot s divided by the square root of 3 in this case, always the count of these things, which is going to be 3 in this case. So this tells us where to round. Let's come up here. Well, first of all, let's copy this over. And think in terms of this is rounded down under, is it under data? Is it under, oh, it's under home. We're going to round that down to 1 significant digit. Whoops, wrong way. And then this number is rounded down to the same level as that. So 0.04, it's in the hundredths place, so that stays in the hundredths place. And this one really doesn't matter, but I'll round it down a little ways too. Same thing with this one, we got a 0.01, so, and it's already rounded to the 0.01. This one is going to be rounded down to 0.3, and this should be also rounded to the 10th place. So in reporting, we would say L is 12.62 plus or minus 0.04, And the width, we don't have enough room for this. Whoops, come on, come on. Let go of that. Okay, you get that, move that over, and then you say that is, quote, 7.66 plus minus of 0.01. So let's go through the equations in the lab for a moment. It says L bar equals 1 over n times sigma 1 to n of L sub I. This means L1 plus L2 plus L3 in our case, because n was 3. If n were 5, it'd be L1 plus L2 plus L3 plus L4 plus L5. Same thing with the width. The average width, which is denoted by that bar there, is the sum of the widths divided by the number of widths. This is the equation for standard deviation of, or sample standard deviation. Notice the n minus 1 here specifies, usually we refer to this as S sub x, or this would be S sub w and this would be S sub l for the standard deviation of the lengths and the standard deviation of the widths. That n minus 1 indicates that it is a sample standard deviation with this n minus 1 in the denominator instead of a population standard deviation. Let me actually take a moment to actually use this formula for the case that we just did. We've got these lengths here of 12.55, 12.6, and 12.7. I'm going to come down here and copy that. Paste special. No? No? Okay, I just copied them number by number. Now, for these, I want L bar to be equal to, well, actually, let's do L minus L bar. Is that our equation? Hold on. Yeah, we want the sum of Li minus L bar, and then we want that squared. So yeah, let's make several different columns. We'll make one column for L bar here. So it's equal to average of these three guys. Now, if I copy that down, the 16 and 18 will increment, so I need to put a $sign in there to keep those things from incrementing. And if I do this right, it should stay the same all the way down. Okay, good. Okay, so now L minus L bar, and it'll be equal to this minus this. And you'll notice I'll be getting some negative numbers and some positive numbers. Then I will take parentheses L minus L bar quantity squared. So that will be equal to this squared. Now I've got only positive quantities. Then I want the sum of these. So equals sum of all of those is 0.01167. So now we've got sum I equals 1 to n of L sub I minus L bar squared. Now I just need to take that divided by n minus 1, which in this case is 3 minus 1 is 2, and take the square root. So square root of that quantity, the square root of this quantity here divided by 2. So the standard deviation dot S equals the square root of this quantity divided by 2, 0.07638. So if I've done that right, it should match this value here. Let's add a few. 0.07638 0.07638, so it came out to be the same. If we wanted the standard deviation dot p, it would be equal to this it would be equal to this quantity, square root of this quantity divided by 3, which instead of using the 2 on the bottom, we use a 3. So you can see it is far, far, far more easy to type in stdev.s. So here in equation 3, we took our sample standard deviation divided by the square root of 3 to get our standard error. And then coming down here, we see area is equal to length times width. And they specifically take the mean length times the mean width here. So, and then they have this strange expression for the standard error. And I will describe a little bit of how that expression comes about on paper. I'm going to draw a little square or rectangle. Here is our rectangle, and here is L, and here is W. And let's also include this area, which is L times delta W, and this one is W times delta L. So we have a little W and delta W down here, and an L and a delta L over here. And then we have this teeny little thing here, which is delta L times delta W. So if we want to just think about the area of this plus this, we can actually kind of think of a vector. And this might be a little weird way of thinking of it, and I'm not sure if this is the best proof, but we've got a vector W delta L, comma, L delta W. That's our vector. And you remember that the way we find the magnitude of a vector, we'll find the magnitude of the vector of the delta A vector by taking this square root of this quantity squared plus this quantity squared. So if we had square root of W squared delta L squared plus L squared delta W squared. So that is our delta A, and we just replace the delta L's. Replace the delta L with an alpha sub L and the delta W with an alpha sub W. And that's how equations 5 and 6 are essentially derived. So let's find alpha sub area. Well, figure out sigma area first. And alpha sub area next. And to get the sigma of the area, we'll take the mean length, square root of, let's do this way, mean length times standard deviation of the width, quantity squared, plus the mean width times the standard deviation of the length, quantity squared. Sorry, it's getting off here. And I think that is it. It didn't like it because I didn't put a parentheses here. Okay, stop bothering me. Okay, parentheses. All right, and then the alpha sub A is going to have to do with the standard error in the length and the width. So equals square root of quantity parentheses length times the standard error of A quantity squared plus parentheses width times the standard error of the length quantity squared, and then we'll put a parentheses on that and gives us 0.36057. And what about the mean area? Equals the mean length times the mean width, and so we will bring this down to one significant figure. Whoops. And this down so that this is in the tens place, so this must also be in the tens place. There we go, 96.6 area is 96.6 plus minus 0.4. There we go.